Now we're starting session 1, data supporting PTD. So it is my pleasure to introduce Dr. John Gambatis. Dr. Gambatis is a renowned PTD researcher and expert and will be the moderator of this session. Dr. Gambatis is a professor at the School of Civil and Construction Engineering at Oregon State University. John, the session is yours.
Thank you, David, and thank you for the nice introduction to the workshop. And welcome, everybody. Hopefully you can hear me okay. I have the pleasure of starting off the workshop here with 2 speakers and a session that I think is important related to, as David said, data supporting prevention through design. So I'd like to start that here. I'd like to also just say thank you to David and Ed for setting up the workshop and continuing the workshop series. As David said, it's an important topic that I think we need to address and continue to grow and develop and implement and diffuse throughout the industry. So thank you to both of you. We have 2 speakers today, and you can see their pictures there, Matt Hallowell and Andrew Griffiths. So as David said, we'll have their videos, and then we will have some Q&A after the videos occur. I wanted to just remind you that if you have questions that you would like to ask of the presenters, please put them in the Q&A. You can do that, and we will get to them. I will monitor that, and we will get to that during the Q&A session after both videos. So without further ado, I'd like to introduce the first speaker. Next slide. First speaker, you probably know very well. He's a professor at the University of Colorado at Boulder and done quite a bit of work in the safety area. And he is very active in research, and his organization CSRA is one of the sponsors of the workshop here. So Dr. Matt Hallowell. And as you can see there, his bio, I'm going to read a few things here. He's the President's Teaching Scholar and the K. Stanton Lewis Professor of Engineering at the University of Colorado. Nice honors there. Executive Director of the Construction Safety Research Alliance. And he has degrees in civil engineering and focusing on construction engineering and also occupational safety and health. He's worked in construction, even as a laborer, project engineer, quality inspector, and I have firsthand knowledge that he was a pretty good PhD student as well. So welcome, Matt. With that, we'll run his video here. So go ahead and start the video.
Good day, everybody. My name is Matt Hallowell. I'm a professor at the University of Colorado at Boulder, and I am the founder and executive director of the Construction Safety Research Alliance. Today, I'm going to give a presentation on energy-based hazard recognition in design. This particular topic really focuses on seeing if we can translate some of the lessons that we've learned about hazard recognition during construction further up the project delivery process and all the way back into design. And so before I get going, I just want to give a shout out to Arizona State for inviting me to give this talk, and thank you all for attending with me. So without further ado, I'm going to launch in, but I'm first going to tell you a little bit about the research group that I run at the university. So I started the Construction Safety Research Alliance about 3.5 years ago, and the vision for this group is really to eliminate serious injuries and fatalities. And towards that end, we have industry practitioners who collaborate with our academic team. And so we have about 78 different companies who collaborate with us, and our academic team is growing. And the nice thing is that the academics bring the knowledge of how to do research in a scientifically valid and reliable way. And our industry practitioners have rich knowledge of the context, of the challenges that are faced in the field, the opportunities that may exist, and access to great data. So it's a very nice collaboration and results in fruitful research. And so about this topic, I want to start with just a few things that I've learned about prevention through design. A lot of this I learned from my advisor, John Gambatese, who coincidentally is moderating this session for us. And one of the things that I've really seen is that there's a ton of great research showing the potential benefits of prevention through design. I think there's no question at this stage of research that we know that prevention through design makes a huge impact. However, depending on where you are in the world, there are some pretty significant barriers to the implementation. And so even though there are all of these studies that show that prevention through design is a really good idea, a lot of government funding to improve prevention through design out there, we still realize that there are some significant barriers. And so some that I'm aware of, for example, is, in the United States, we have the OSHA General Duty Clause, which essentially puts the responsibility of safety onto the employer. And oftentimes, the architect and engineer, the AE firm, really doesn't have too many employees out there in the field. So the primary responsibility for safety rests on the contractors and subcontractors, yet we know that the architects and engineers have great influence. The second thing, in connection with this, is that we oftentimes deliver our projects through a design, bid, build, lump sum delivery. And so when we do that and we look at the OSHA General Duty Clause, there really is a lack of economic incentives for designers to really design for safety. Now, with the construction design and management regulations there, we know across the pond, some of these have been addressed, but here stateside, we realize there's a lot of, there's some lack of incentives out there. We also we don't quite have that much safety education in architecture and engineering courses. I think we're trying to change that, but we need to be better. And then finally, whether it's a proper thing or not, or whether it's true or not, there is some fear of liability from the design community who worry a little bit about where that might place them in terms of responsibility for folks that they don't have too much control over. And so I say all of this not to kind of put a dark cloud over prevention through design, but just to emphasize if it is really as impactful as we our research shows it to be, we need to make prevention through design as easy as possible. And I would argue that means making it easier for designers to recognize hazards as inherent parts of their design. So we want to make as many hazards as possible easy for people to see and anticipate as early in the project delivery process as possible. And so I want to also kind of wrap up this slide just by saying, most of the tools and resources that we've created in the academic community really focus on trying to create a list of as many hazards as possible, right, related to particular design components. And I would argue that that's a great idea and we should have that, but we should also have some tools and techniques that allow people, designers, to think more broadly about the hazards in their designs and give them the ability to anticipate hazards that might not be on the list, right? So especially as technologies change, as our work methods change, as design configurations change, we need to make our designers, our construction managers, our planners, our construction workers more nimble in their ability to recognize hazards. And so I want to share with you a few lessons that we've learned through our hazard recognition research in construction. So for over the last 8 years or so, I've been doing a lot of work in hazard recognition during the construction phase. And it really started with about 2 years that our team spent in the field collecting some data, trying to answer some pretty basic questions. Number one, how good are we at hazard recognition? In other words, how, what proportion of hazards are we able to see and anticipate before work begins, right at that work phase? Not all the way back in design, but right in the field where the work is taking place, where we can, we know what the weather is going to be, we know what materials we're using, we know what the configuration is. Question number two is, in addition to how good are we, what types of hazards do we see and which ones do we miss and why? And then of course, third point is we want to see how we can get better. We want to learn how we can improve that hazard recognition skill. What we found in our research, and this has been validated by other folks in other regions of the world, is that construction workers are able to identify and plan for about half of the hazards that they actually face, right? So this is without any other tools or techniques, but 45% is the average skill out there, which means about half of the hazards go unrecognized in planning, and it's really left to the construction crew to identify those hazards as they emerge through the work. Now, that tells us what's going on in the field, but our laboratory research and the neuroscience in particular helped us to understand why. Why do we see some hazards and miss others? And what you're seeing on the screen here, in the middle part there with the crazy hairnet looking thing, that's called functional near infrared spectroscopy, or FNIRS for short. Very fancy term for technology that sends a small pulse of infrared light into the brain, and the sensors measure how much light bounces back, and variations in that information in terms of how long it takes the light to come back and how much light comes back tells us where oxygen is being consumed in the brain and how much. And in other words, you can see an fMRI image on the far right. That's a very detailed version of a brain scan, and that shows us essentially what part of the brain is active and how hard the brain has to work, right, in terms of effort. And what we learned through that research, and this applies in design as well, as you will see in a moment, is that almost all of the hazards that people identify easily in their first scan, the ones that come to mind, are identified in an area of the brain known as the amygdala. That part of the brain is responsible for fight or flight response, right? So anytime you're processing an intense emotion, the physiology that goes along with it, your voluntary and involuntary movement, that tends to be processed here in the lizard brain, or the amygdala, the core primal instinct part of your brain. And so a story that I like to tell here is, imagine that you're walking into your house and it's late at night, and one of your friends or a family member is there, going to startle you as a prank or something, and they jump out. Well, you're going to have an intense emotional experience, right? Fear and maybe a little bit of anger. It's going to come with a physiological response. Your adrenaline's pumping, your heart rate goes up, your blood vessels constrict, and your pupils dilate. And then you might even move back, right, and get in your ready position. Well, the interesting thing is almost all of the hazards that we process, easily are processed in this part. This is a low-cost part of the brain, right? The hazards that we tend to miss are processed in the amygdala, and that's the part of the brain that's responsible for complex thought. So the things that we've learned, experienced, our education, our ability to solve logic problems and communicate the results, these are all cerebral tasks that require comparatively way more mental effort, about 100 times the mental effort. And the hazards we miss are, missed here in our brain's infinite desire to be as efficient as possible. So what we found is actually by training people a little bit more on what a hazard actually is, right? And by giving them different categories of hazards to think about, we can improve their hazard recognition skill dramatically. So this is based on a pretty simple but very powerful concept. And that is that every injury, not every illness, but every injury, is the result of some undesirable contact between a human being and an energy source. So that could be something falling on somebody, that would be gravity, something striking someone like a piece of mobile equipment, that would be motion, tension, compression, rotation, vibration, those would be mechanical hazards, and so forth. And what we found is by showing people the energy wheel and having them think more broadly around different categories, we can really expand people's understanding and ability to think more broadly about the hazards in their environment. Now, interestingly enough, gravity and motion hazards tend to be processed in that lizard brain, right? The amygdala, very easy to process. And almost all of the hazards a crew will identify and discuss are gravity and motion. The hazards that we tend to miss, the more cerebral hazards, tend to be things like unmoving mechanical, like tension and compression and torque, pressurized systems, radiation, things that can change temperature, for example. These are all more cerebral hazards, and they tend to be missed unless we give the brain a reminder to think of those types of hazards. So this energy wheel is simply what's called a mnemonic. It's a set of reminders to think about hazards that the brain would otherwise skip over. Now, our big question, though, is this worked really well in the construction phase. What we found is, you can see in the shaded area, that was the hazard recognition skill before any energy wheel training. And that's where that 45% came from. What we did find is by training people on the energy wheel through a series of experiments, you can see published in the study at the bottom of your screen, is we found that the energy wheel improved hazard recognition by an average of 29%. So a pretty dramatic improvement, and you can see that we were pretty good at gravity, motion, mechanical, electrical, but comparatively pretty poor at pressure, chemical, temperature, radiation, and so forth. And so the energy wheel helped us to think more broadly. Now, our big question, though, is, does this energy wheel or energy-based hazard recognition help us in design as well, right? I think we can theoretically see how it could improve, but we really wanted to test that. And you can see I'm going to cover the results of a paper that was published in Safety Science. One of my former students, Daniel Hansen, and I published this several years ago. So this is accessible if you're interested. And what we were really seeking to do is answer a few research questions. Number one is we wanted to understand, what is the typical hazard recognition skill and design? We knew that in the construction phase, with the benefit of all the information about how the work is going to be done, where it's going to be done, the design is for the most part substantially complete. We knew that was 45%, but how good is it in design, right? All the way back where we don't have all those benefits. And I'll give you a spoiler alert, it's not 100%, right? The other question here is, what proportion of hazards are actually recognizable in design? Now, we've made a pretty big assumption in most of our academic research, and that is that if a hazard will be present during the construction phase, that designers should be able to anticipate that, right? Now, we've learned even during construction, at the pre-job phase, right before work begins, that not every hazard is reasonably identifiable even then, right? Some things emerge throughout the work period. So our question is, what's the best skill we could really get, right? What hazards are recognizable and which ones aren't? And then finally, to what extent does the energy wheel or energy-based hazard recognition really improve our skill? And so, in the design phase. So I'll show you a little bit about how we collected our data. So we are known for running experiments in my lab. That's one of the fun things that I enjoy doing. And the first thing we did is we actually went and visited some sites. And we observed construction work for a module, right? And so when I say a module, I'm talking about a package of work that takes somewhere between 3 and 5 days to complete. So it could be installing roofing membranes, it could be building an atrium, it could be pouring a concrete footer for the foundation, modulated portions of work, right? And what we would do is we observe that work, and we would also obtain the plans and specifications for that work, right? For this ongoing work. And we got that data for 12 modules, right? So we observed the work period and we obtained the plans and specifications. And during our observations of work, we identified as many hazards as possible. So the students coded each other and did inter-rater reliability, and we identified as many hazards as we possibly could by observing that work in real time. And we'll call that the truth, right? From there, what we did is we took the plans and the specifications, only the plans and specifications, and we gave them to 47 designers. And we asked them, we did a simple experiment with them. We took the 12 modules, and we would, for each designer, we would randomly select 6 that we would give them before any training. We'd give them the plans and the specifications and said, for this particular module that you see in the design and spec'd out here, what hazards could we anticipate that there may be during construction? Then what we would do is we would give each one of the designers energy wheel training. And then we'd give them the remaining 6 modules that they had not yet seen, right? So this is a randomized experiment. The order in which they saw the modules was completely randomized, 6 before, 6 after. And what we did with that data is we first looked at the hazards recognized before any training and the actual hazards that were present to measure the skill, right? So the proportion of hazards that these designers were identifying and able to anticipate. The second question was to take the hazards after the training and identify which of those hazards that were actually taking place were able to be identified by at least one designer. So even only one designer anticipated the hazard, we had marked that as identifiable. If 0 designers recognized that hazard, then we marked it as unidentifiable, right? And so that helped us answer research question 2. What proportion of the hazards are actually reasonably identifiable as measured in these 12 modules? And then finally, what we did is we took the hazards recognized after the training and compared them to before. And that allowed us, because we ran a randomized experiment, to measure the impact of the energy wheel training. And that helped us to essentially measure that skill improvement. Now here's what we found. Related to research question 1, the average hazard recognition skill among the designers was 38%. So a far cry from 100%. So that means that not every hazard was identified and anticipated by designers naturally, right? Only about a third of all of those hazards were identified. Research question number 2 is we found that about 76% of all of the hazards are reasonably identifiable. In other words, they were identified by at least one of the designers. There were 24% of hazards that nobody anticipated. What that means is that's really our ceiling, right? We need other processes all the way down the project delivery phase to address the other 24% because they're simply not reasonably identifiable at this stage in design. And then finally, in research question 3, the energy wheel improved the hazard recognition skill by an absolute amount of 10%, meaning we went from 30 to 40%, right, in one group, and 40 to 50% in another group. If we look at it on a relative basis, going from 30 to 40% is 27% compared to the baseline. So it's quite an improvement compared to where we started from. And I will show you based on the table that you see at the bottom of your screen. We did break up our designers into 2 groups. Group A had no construction experience at all, so no field experience. And Group B were designers who did have construction experience. And we did anticipate, and you can see from the data, that Group B, those with construction experience, had on average better performance, both in the baseline phase and in the post-intervention phase. What we found also, if you look in the baseline, is that Group A improved from about 30% to about 40%, and Group B improved from the baseline to post-intervention from about 43% to 50%. What's really interesting to me too is if you compare the baseline of those with experience to the post-intervention to Group A, is they're about the same, right? In other words, if you don't give somebody with experience an energy wheel or any other way of thinking about hazards, they're about equal to a designer with no construction experience who does have the tool. So it's very interesting. Obviously, the best is to have some construction experience and have the energy mnemonic for you. And so that's where you see in Group B, that's the 50%. So, few conclusions. Number 1 is that not all hazards are reasonably identifiable, right? We just can't recognize every single hazard in the design phase. So we do need to think of prevention through design being part of the solution. I suggest, based on what I've observed, that we use a combination of both the list-based approach, our inventory of all of the hazards associated with tasks, but also think about giving people something like the energy wheel so that they can think even more broadly of hazards that might not be on our lists. And then finally here, construction experience is essential and irreplaceable. It's going to be, we can improve skill just by simply giving our designers a bit more experience in the field. And so I think of, this tool and technique and prevention through design in general as being part of the solution, right? It's going to be part of the project delivery process. We want to give our designers as many tools as possible so they can not only think about work as we imagined, right? How we imagine the design being built, but help them anticipate how work actually gets performed by thinking, again, more broadly. So I want to thank you for taking some time with me today. I enjoyed this session and I look forward to the Q&A. Thank you.
Wonderful presentation, Matt, and a lot that we can learn about prevention through design. And importantly, you've set the stage for the need for data. And we realize that as we do our research, that we need good data about what designers can do and what they can't do, and perhaps what their potential impact is on safety. So thank you very much. Just a reminder to everybody, we